Hello, everyone. Welcome to pre-lecture 16. We're going to do some more acid-base practice and also talk about what buffers are in this lecture. Okay. So before we get into that, though, I wanted to bring up one thing that we hadn't yet covered, which is periodic trends in acid strength. And so, reminder that we, of course, have strong acids and weaker acids. This ultimately relates to the bond between a hydrogen atom and whatever it's bound to. So we could just call that X as a general placeholder, right? The two things we're really balancing there are the bond's polarity and its strength. So the more electronegative an atom is, the more polar a bond will be, which leads to a stronger acid. However, we have to balance that with considering atomic size. And so the smaller an X minus atom is, the stronger a bond it will have with a proton. It's H+. And so that means that it's going to be harder to break, which leads to weaker acids. And so that's why we get things like H2O and HF, where both oxygen and fluorine are obviously very electronegative, but they are also very small relative to the next rows down on the periodic table. That's why water and HF are weak acids, whereas when we get to HCl, HBr, HI, those are both electronegative and big, so they are strong acids. And then we see if we go down column 6, we end up getting stronger and stronger acids as our atoms get bigger and bigger. Okay. So there is another class of acids that we haven't quite yet talked about called oxyacids. And so you've already seen these in some regards. For example, perchloric acid, HClO4, one of our strongest acids. And what it just is it means our hydrogen is going to be bound to an oxygen, which is bound to a central atom that has other oxygens yet coming off of it. And so we end up getting things like this, where we have, again, some sort of oxygen-based acid with a central atom, and those are our hydrogens. Other examples of this might be something like phosphoric acid with phosphate, sulfuric acid, H2SO4, nitric acid, HNO3. Those are all oxyacids, right? Okay. So changing gears a little bit, I know last class we started to talk about how we can calculate pH of salts. And so I wanted to provide another example of that. In this case, we're going to calculate the pH of a solution that is 0.250 molar in sodium chlorite, so or hypochlorite rather. So this is bleach, in other words. And we have a Ka given to us of 2.9 times 10 to the negative 8. And so before we begin, we can even answer this first question. Will the solution be acidic, basic, or neutral? And so we're given a Ka of HClO. We're told that the thing that we're actually starting with is the sodium version of that. So all we've done is replace this H with an Na, right? And anytime we replace an H with an Na, what we're doing is we're going from an acid here, HClO, to a base here with NaClO. So we're adding a base to water. That means that our final pH should have a basic solution, right? It should be greater than 7. So we can always use that as a conceptual check to get to the end. The other thing we should always do to start equilibrium problems, write out the relevant chemical equations, as well as our K values. And so if we're starting with sodium hypochlorite, NaClO, that's a salt. So our first step, if you remember from last class, is to have it dissolve. So we end up with Na plus, aqueous, and ClO minus aqueous, right? We know, or hopefully we remember from last class, Na plus, that's going to be the conjugate acid of a strong base, sodium hydroxide, is not going to affect our pH. That would only lead to things being neutral. However, ClO minus can react with water. And so ClO minus aqueous plus H2O will be in equilibrium, right? Because this is a weak base and a weak conjugate acid, HClO aqueous and OH minus aqueous, right? Also, I forgot to include water, pure liquid there, right? So then we can write our K values or our K expression, and that should remain products over reactants. So products are HClO, hydroxide minus, and ClO minus on the bottom, right? The question for you is, are we going to use Ka or Kb? We're given a Ka value, but hopefully you recognize, again, ClO minus, that's going to act as a base. So we're going to need to find the Kb value, okay? And how we would do that is 1 times 10 to the negative 14th is equal to Ka times Kb. And since we have the Ka value of 2.9 times 10 to the negative 8th that is given to us, we can do 1.0 times 10 to the negative 14th divided by that value. When we do that, I got a Kb value equal to 3.45 times 10 to the negative 7. Then, since this is an equilibrium problem, as long as we are in equilibrium, we can build a nice chart. And so that's what I'm going to do. Build a nice chart. We have a 1-to-1 ratio between our sodium hypochlorite and our hypochlorite that's going to form. So I know that basically we just start with the same concentration there of 0.25 molar. Water, pure liquid, don't have to include. We're not told anything about the concentration of our reactants, and so we don't include those. From there, our change, if you look at our coefficients, minus x, plus x, plus x, and then our equilibrium row, we just combine things. So 0.25 minus x, and x. Finally, we can, well, not finally, I guess, but our next step is to plug in these values into our Kb expression. Right, so, and I'm also going to plug in our Kb value that we calculated. So 3.45 times 10 to the negative 7th is equal to x squared over 0.25 minus x. This is an x is small, right? The reason we can do that is because the Kb exponent is smaller than times 10 to the negative 4th times 10 to the negative 7th. So we can use our x is small approximation. So we'd multiply each side by 0.25 and then take the square root in order to figure out x. And so skipping a couple of those steps, determined x is 2.94 times 10 to the negative 4th. Okay, so that's what our x value is, and we can always look back at our ice chart to see what x is actually equal to. So x is equal to hydroxide, it's also equal to HClO. And so the one we care about as far as determining the pH is going to be our concentration of hydroxide, H minus. So if we take the negative log of that concentration we determined, that 2.94 times 10 to the negative 4th, and then we would get the pOH value. And so for the pOH, I got, let's see, 3.53. Then if we do 14 minus that pOH value, I got a pH of 10.47 for our pH. Hopefully that is what you got too. You're calculating along. If you have any questions on that, of course, feel free to let me know at the beginning of class, but that is how you would do that problem. And that will be all for our pre-lecture today. Hope it was informative, and I will see you in class soon.